Hi everyone. So this is a continuation of some of the stuff we have studied uh, in our last lecture. So we did discuss about the classification of kinematic pairs, or the word being written as a pair in most of the textbooks. So we have so I will just go a little bit of revision of last lecture. So we have discussed the division of kinematic pairs, which was basically the lower pairs and higher pairs. So the lower pairs are further classified in six different groups or six different pair. So these were individually discussed, the nature of motion and as well as the degree of freedom and the variables as well. And then it was further discussed uh, the higher pairs cannot be classified as such because there is a large variety of those pairs. So that makes irrelevant to classify. And it was discussed that we shall treat each separately as it arises. So the higher pair would be discussed individually rather than having such classifications. And all of these pairs was summarized in one of this table, uh, including revolute, prism, screw, cylinder, sphere, flat. So the important thing which I suggested you to remember, I would say, is when we say, let's say if it's a screw pair, so it has these two variables, but they are dependent to each other. So that's why we can just use one of that one, and it has 1 degree of freedom and relative motion is helical basically. And when we say, for example, the cylinder, it has same parameters, but both are independent and it has 2 degree of freedom. So the sphere has represented by S and as three variables. So that's why the degree of freedom is 3 as well. A flat pair, which is quite uncommon, uh, it has also 3 variables and degree of freedom is also 3. So these were the summary. Same goes with the revolute and prism as well. So the variables and the degree of freedom is also mentioned. So we need to make sure you, you should be familiar with these ones, because as they come along we will use especially the symbol and the degree of freedom and the variables basically. So with regard to that, we will continue now to the next one. So the next definition is about mobility or degree of freedom of mechanism. So degree of freedom is quite well known term, but the mobility can also be used, and in fact the essence of both is same. So if the degree of freedom or the mobility both are same, so one of the first concerns in either the design or the analysis of a mechanism is the number of degree of freedom, also called the mobility of the device, because the way it moves, this will be degree of freedom, but this would also be termed as the mobility of the device. The mobility of a mechanism is the number of input parameters, usually joint variables, right? So once again, the mobility of a mechanism is a number of input parameters that must be controlled independently to bring the device into particular posture or position. So the important thing is it must be controlled independently, which is also a definition for degree of freedom basically. So the for degree of freedom are basically the independent parameter, which we have discussed over here as well. I will just go over there. So for example, in screws pair, these were not independent, so that's why it has just 1 degree of freedom, or the mobility is 1. But in this case, same parameters in cylinder sphere, you have same parameters or a pair variable delta s and delta theta, but both are independent, so that's why they have a 2 degree of freedom. So ignoring for the moment certain exceptions to be mentioned later, it is possible to determine the mobility of a mechanism directly from a count of a number of links and the number and types of joint comprising the mechanism. So for example, what did this last sentence means? Uh, there is a qualitative way you can look at the mechanism, saying how number of degree of freedom would be there. But now we will move toward a quantitative method where we will try to establish an approach where we want to find out or link the uh, variables, for example, the links and the joints, and try to find out the degree of freedom or the mobility of the uh, mechanism basically. All right, this was very interesting, some of these examples. So if we denote the number of single degree of freedom joint, J1 as a J1. So just remember, this is a term we will use quite a lot. So this is one of the equation where you have a single degree of freedom joints as J1. So J1 is a single degree of freedom joints, and the number of 2 degree of freedom joints are J2. So any joint which has 2 degree of freedom will be J2 basically. And the resulting mobility M, which is basically degree of freedom as well, of a planar N-link mechanism. So N-link, N is basically the number of links, right? So you see this equation, you from any mechanism you can work out how many number of links are there, how many 1 degree of joints, how many 2 degree of freedom joints. So you use this equation and you will work out what will be the mobility of the mechanism. So the sole purpose of this equation is to find the total degree of freedom of the mechanism, or you can call it as the mobility of the mechanism. So this equation 1.1 from same book Shigley is called as a Kurzbach criterion for the mobility of a planar mechanism. So this planar mechanism is being used quite a lot here. Planar means, of course, it is moving in one plane, right? Plane mean X, Y, for example. So it's not 3-dimensional. So it's a 2-dimensional mechanism basically. So its application illustrated for several example in figure 1.3. So this is figure 1.3. So for example, this is one of the mechanism where uh, the value of M is being determined by using this equation. I will go through one by one. So just for your practice. For example, here the number of links 1, 2, 3 in diagram A. N is 3. Number of single degree of freedom joints are 3 as well, because 1, 2, 3, they are all single degree of freedom joints. So they don't have the 2-dimensional movement, because 1 degree of freedom means it just have circular or revolute point. This is kind of like pin joint where you have just revolution. So that's why each individual joint is able to do the similar kind of phenomena. So you have the angular movement. So J1 is equal to 3 and J2 is equal to 0, because there is no joint here which has 2 degree of freedom joint, right? And you just plug in these 3 variables over there, because we need 3 variables here, and you work out. So it has a 0 mobility. So it cannot move anywhere basically. It does not perform any movement here. So that's why its mobility is 0, or the degree of freedom is 0 for whole mechanism. So when I say, so just make sure you understand this. There are 2 things. One is a degree of freedom for a single joint. So J1 is the number of degree of freedom for the joints basically. Yeah, so you say 2 degree of freedom joint is J2, single degree of freedom joint is J1, but the whole mechanism, how many degree of freedom is there, that will be called as a mobility of the mechanism, or the degree of freedom of the mechanism itself. So if you go to the next one, so it's very clear. So the next one has this is more like a slider crank mechanism, because this one is sliding and this one is rotating. So again, this has 4 links. This is link 1, this is link 2, this is link 3, and this is link 4, the slider. And all joints here are single degree of freedom joints. Why? Because, for example, the slider moves on a flat surface is just one dimensional rectilinear motion. So it's just that's why it is single degree of freedom joint, and all other are revolutionary joint, revolute joint, where just one angle is enough to explain as an input parameter. So you just plug in, you work out the degree of freedom or the mobility is 1, which makes sense because this is just moving in one dimension. So one directional movement is there. So similar thing is here. This is a 4-bar link kind of mechanism. So where you have 4 links. So 1, 2, 3, 4, and you have 4 joints, 1, 2, 3, 4. So all joints are basically single degree of freedom, right? Why? Because you just require one angle. So that's why that's the case. And there is no 2 degree of freedom joints. And you plug in all these variables in the same equation 1.1 by Kurzbach criterion, and then you work out what will be M. The mobility is 1 basically in this case as well. The last one is interesting. So where you have 5 links, 1, 2, 3, 4, 5. And J1 is equal to 5 also, because the pin joint typically, because in all cases was same. So 5 J1 as well. And J2, 2 degree of freedom joint, nothing is there because there is no joint which has 2 degree of freedom. So you plug in and you work out what will be M, and that's 2. So you can imagine if you try to move it, so it could have a different kinds of rotations basically to this one, for example, because the links are connected in such way. It could, for example, you want to move this end, so it has a different phenomena. If you hold this one and move this one, so it has a different, so it has the possibility of double movement, which is not possible in none of these ones. So mobility is 2 in this case. I haven't seen it, but I think if, let's say, if you Google it, 5 joint link animations, you might understand quite well how the mobility is 2 here. All right. So yeah. So if Kurzbach's criterion yields M greater than 0, the mechanism has M degree of freedom. If M is equal to 1, the mechanism can be driven by a single input motion to produce constrained, uniquely defined motion, because when M is 1, so this mobility is 1, degree of freedom is 1. So we just need a single input motion. This is interesting. So that what they mean, the meaning of single degree of freedom. Basically, we need a single input motion to produce constrained motion. 2 examples are the slider crank linkage and the 4-bar linkage shown in figure 1.3, B and C. So these two, B and C, are the single degree of freedom basically. If M is equal to 2, so this one, the 2 separate input motions are necessary to produce constrained motion for the mechanism. Yeah, so you need 2 separate independent input motions. That's important. So if you have 2 independent motions, that's why the mobility is 2. Then we have such a case is 5, that is shown in figure 1.3D, right? So if the Kurzbach criterion yields m is equal to 0. Yeah, so this is a special case now. So if let's say, I will just show you the equation. You plug in numbers in such a way that you end up having a 0m. So what does this mean? The mobility is 0, right? So the mobility is 0 basically. So what in that case, in figure 1.3a and 1.4a, so the motion is impossible and the mechanism forms a structure. So this is a very good definition of a structure. By using Kurzweil's relation or criterion, you can work out if this is a mechanism or a structure. So structure is different. You need to understand. Structure is the one where there is no mobility, because mechanism is a purposefully designed in such a way where we need a movement or the mobility. But let's say if you don't have the mechanism, that the links are joined in such a way, the mobility is returning to be 0. So means it's not a mechanism, it's a structure. For example, this one, 1.38. So 3 are linked. You cannot move it actually. This is just a structure. So what is it? You have n is equal to 3, j1 is equal to 3, j2 is 0. So you plug in and you have mobility 0. So it is just a structure. It's not a mechanism. And same goes here as well. So you have 5 links, 6 joints basically, j1 members, and then you have the j2 which is 0 and m will be 0 as well. So it will also not move. So there is no movement over here. Okay. And the next is quite interesting case. If the criterion yields m less than 0. So same. So this equation, if you plug in numbers and then you end up having m as a negative number. So what does this mean? Then there are redundant constraints in the chain and it forms a statically indeterminate structure. An example is cited here. So now I'm quite sure you are well aware of statically determinate and statically indeterminate structures. So so for example, this is one of the example we have n is equal to 6. So you have 6 links. The joints are 8 for each individual link. We need to consider the joint. So that's why we have 8. If you plug in, you have m is equal to -1. So what does this mean? This is structure. This is not a mechanism. But in addition to structure, it is statically indeterminate structure. So you cannot determine it basically. You cannot calculate. Yeah. Okay, so that must be the definition of structure. For example, we can work out by using the same relation. All right, so now we have a couple of examples. So which are being asked to find out the mobility of planar mechanism. So these problems are the planar mechanism. So it's like 2-dimensional movement in one plane, for example. So it's not 3-dimensional. So you see there are the shape is like that. So it has some of the links. So for example, this is link, 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 and the joints as well. So some of the joints we need to identify. So the steps would be first step should be you need to identify how many joints are there, and it's always good practice. I will show you in the next slide to write on the diagram saying this is one of the link, for example, this is another link, this is another link, and as well as you write down what are the joints. So if it's a J1, J2 or something like this, so you need to work out and write those joints as well. And then you just use this Kurzweil relation to find out the mobility of the mechanism. So we will solve this one now. So this is example. So the solution is already provided in the book. So I have taken the snapshots from the book. If let's say, is there anything missing? So you can just visit the book, this Theory of Machine by Shigley, and you can find the extra information. So as I said, the first thing should be you need to identify the links. Let me go through this. So for example, the static point is considered as if one link. This is one, this is one. This is link two. So this is link 2, and this is link 3. This is link 4. This is link 5. And that's it. So we have 5 links here. Just don't confuse this one. This is not one of the link. This is basically a slot. This is a slot within link 3. So it's like hollow from, and there is a one joint here which is sliding over here basically. Yeah. So the link numbers and the joints types of the mechanism are shown in figure 1.7b. So this is 1.7b. The number of links is 5. The number of lower pairs is J1 is equal to 5. Let's find the J1. So this is J1. So 1 degree of freedom. So it just can be defined through one angular movement. This is also J1. So it's just like rotary revolutionary pair, revolute pair. So this is also revolute pair. This is also revolute pair. This is also revolute pair. The only thing which might be a little bit confusing for you, but because this is an example, so you can try to build your concept from here. So this one could require 2 degree of freedom to define. Why? Because this mechanism moves, the link 3 moves up and down, or link 5 can move up and down. You see, within that single joint at this particular point, which can be defined either by movement of 3 or movement of 5, and both are independent. 3 and 5 are not linked together. So both are independent. So that's why this joint should not be considered as a J1. So it should be considered as a J2. So that's what he's saying. And the number of higher pairs is J2 is equal to 1. Yeah. So then you just plug in the numbers. So you have n is equal to 5. Single joints is 5, and double joints, 2 degree of freedom joints, J2 is 1. So you work out the value of M, which is 1. So note that the Kurzbach criterion gives the correct answer for the mobility of this mechanism. That is, a single input motion is required to give a unique output motion. So basically it's trying to establish or define the definition of single degree of freedom basically. So for this mechanism, you just need one single input motion. So what does this mean basically? I think it's interesting to think about it. So single input motion is required. So to move this mechanism, if let's say you want to move from here, it will do some certain motion, this mechanism. Or let's say you want to move this one, so it will give same movement. Let's say I move this one here, so this one moves here. So what does this mean? So it will, these one move will up, and so whole mechanism will move if I move at this particular point. So single input motion. Okay, now what I do, instead of moving this part, I move from here, for example, I move this part. So now what happens? It will still do the same movement. So what does this mean? Nevertheless, I do movement from here, or I do movement from here or from here, or anywhere actually. So I am getting the same movement. So that's why it is called as a single input motion, which is well enough to explain such mechanism. All right. So for the mechanism shown in figure 1.8, so this is example 1.2. I hope this is quite clear. This one, this was quite relatively simple example. Uh, so we can discuss this in question answer session actually. So for the mechanism shown in figure 1.8a, so this is 1.8a diagram, the number of lower pairs. So what you need to work out, first thing you need to work out number of lower pairs, J1 joints, and the number of higher pairs joints, and the mobility. So basically we need to work out what's the mobility, but of course when you want to find out mobility, before that you need to identify what are the number of links, what are the number of J1 joints, what are the number of J2 joints basically, and using this Kurzbach criterion. So treating rolling contact to mean, so this is one of the assumption, treating rolling contact to mean rolling with no slipping. So wherever there is a rolling, for example, here it's mentioned. So this is rolling part, this is rolling part, and we don't have any slipping. So we call it as a mean rolling basically. Next, he's saying, does this criteria provide the correct answer for mobility of this mechanism? Yeah. So you will see that I think this was the example where Kurzbach criterion is not really good enough to explain. Briefly explain why or why not. Yeah. So what does this mean? Kurzbach criterion is very good for fundamental mechanisms, but sometimes it's not does not provide enough answers actually. So that's why, yeah, we need to be careful when using Kurzbach criterion basically. All right. So in the next slide, the annotated diagram is being shown. So where number of links are independently explained. So this is link 1. So wherever you have stationary, that is link 1 basically. This is link 1, this is link 1, this is link 1. Yeah, it's a good practice to start with the static one basically, so it's not moving. So the second link is classified this one. Third link is this one. So it's one of the disk being rotated apparently. Fourth is one of this middle drum basically, if I say, which is rolling basically the fourth is this one. Fifth link is this one, and then this is sixth link. So basically you see this fifth link has a slot, and this link sixth is moving inside it. And then you have the seventh link. So I think that's all links we have. And now to identify J1 basically. So we have one of the, so at this particular joint, for example, this is because no slippage. So we need to write down this assumption, because if let's say it is a slipping over there, so mean slipping means it is sliding contact. So it is rolling contact, sliding contact. So means it should not be J1 basically then. So it should be J2, because it is two movements is happening actually. So this is J1, this is J1, this is J1 basically. The 2 is mentioned here because it is linked with the base actually, or the middle structure is such way. I think we will have some explanation later on in the last slide. This is also J, where 2 written for, it is J1 but 2 times. I will show you in a while what does this mean 2 here. And then we have one of here. So is this one is moving this, so this is J1, this is J1. So these are all J1s, the single degree of freedom joints, and this one is it J2. So the only here is a J2 is just one here. So J2 is why it is J2 I will explain again, because it can slide in it, and this sliding could happen because this can move in a linear this direction, or this one can move in this direction. So both are independent parameters basically. So if both are independent means they can contribute or they can define this movement over here. All right, so the solution, the links and the joint types of the mechanism are labeled. Yeah, so this was one of the requirements. So A part, so we need to identify the number of links is 7. The number of lower pair is J1 is 9. So I will just go back. So J1 basically this is considered as a 2 times. So that's why we have. So this is 2 times. This is 2 times basically. Why it is written 2 times? Because at this particular joint we have this link attach and this drum attach. So basically these two are joined. So same thing here. So at this particular J1, this joint, this link is joined and this one is joined. So both are linked together basically. So either you can write J1 comma J1, or you can write like J1 here and second one J1 here. So basically one is J1 to do with this bar, and the second one is about this one. So that's why we have the 9, and the number of higher pair is J2 is 1. So it's just one, this one. So substituting the values in Kurzweil criterion, the next one is really simpler one where you just plug in the numbers and then find. So you see the Kurzweil criterion is giving you the answer as a -1 because this is just adding in the numbers, right? We just put the numbers from part A and then work out the value of M. So, however, this answer is not correct. So you see, this is the case where Kurzweil criterion is not defining in a good way. So the Kurzweil criterion does not give the correct mobility of this mechanism. The mobility of this mechanism is in fact M1. Why this? So this is qualitative way of doing it. Why? Just imagine, so it has to move when, if let's say it's moving, for example, it's rotating like this way. So you certainly has, so this moves down because this is drum. So it moves down. So this goes up. So up or down. So this can only go in this direction. So that's why this whole mechanism is providing you such a assembly where only one input is required. So that's why he has given M as a 1 here, right? So the mobility one, because this part can only oscillate in this direction. So if you say with respect to some angle, so you just need some angle to explain, for example, alpha. So only angle can be used to define such mechanism. So that's why it's good enough to explain such mechanism just with 1 degree of freedom. Now the last part of this one, the reason you need to explain. So what is the reason? So what is it? Link 3 and 4 are superfluous. So they are not necessary to the constraint of the mechanism. So they are kind of unnecessary for the constraint. If link 3 and 4 were removed, so this is link 3. So this is one of the drum. This is another drum. The motion of the remaining links would be unaffected. So the movement, because it is nevertheless has to go up and down. So it has nothing to do with these two assemblies. So this drum and this drum. So just imagine if it moves up and down, it can move. It's not necessary because this link is being held here. So if it can surely move like in a circular clockwise, anti-clockwise, and this is being constrained here as well. So it's not like it's just if it moves a freely movement, no, because this has been constrained here, this has been constrained here. So that's why it can only move during these phases. So that's why 3 and 4 are kind of irrelevant. So if you remove those two, the mobility of mechanism using Kurzbach criterion is m is equal to 1. So then answer is right. So Kurzbach criterion not really giving you good answer because 3 and 4, which are irrelevant. So they're superfluous. So they are irrelevant. So that's why we are not getting the good answer. Note that if link 3 and 4 were attached with no special condition, not pinned at their counters, for example, then the mechanism would indeed be locked and the answer would be minus will be correct. So, for example, this is another case. If 3 and 4 are attached and that is not pinned at the center. So they are attached, but they are not pinned at the center. So this 2J1 we have considered. If you don't consider this now, right? So if there is not pin, so it will be just J1 basically. Or this one, same way, if it's not pinned, this is like J1. So then the mechanism would indeed be locked and the answer would be -1. So if they are not pinned, then there is no movement. So that's why we have uh, the right answer, which is -1 basically. Yeah. Yes, so 3 and 4 not pinned at their center. So mechanism indeed be locked and answer is -1. So the answer would be statically indeterminate circuit because it's a locked. So it is of course not a mechanism. So it cannot move. So it is more like a structure. So if it is a structure, means it is statically indeterminate structure which with -1. All right, so we can continue with the next one. So example 1.3. So for the mechanism shown in figure 1.9a, so this is 1.9a, the number of lower pairs. So you need to work out what's the number of lower pairs and the number of higher pairs. So from here you do the same thing and the mobility of the mechanism predicted by Kurzbach criterion. Does this criterion provide the correct answer for this mechanism? Briefly explain why or why not. So it's the same statement. So if we are getting right answer or no, right? So we will do similar steps now again. What are the steps? So these are the links, identification of links. So the link 1 is here. So everywhere where it's static, it's not moving. So this is link 1. So this is link 1. That's it. And the link 2 is basically, yeah. So link 2 is this one, link 3. So this whole triangle is link 3. And link 4 is whole this circular, because the definition of the link was it's a rigid body actually. So it could be any shape. 4 is this one, 5th is this one, right? So this is the 5th link. And of course, you might be seeing this. So this particular part, which has no movement here, no relative movement. So this whole will be as a 1. Yeah, just make sure you understand this. So it looks like it is a separate link, but because it does not have a relative motion, same goes here as well. And for a link, it requires to be a rigid body. So that's why it is, of course, the one of the link only. Yeah, so this goes here as well. Now next is we need to find out the joint. So at this particular interface, or this interface or this interface or this one, all are same and they are called as a J1. So it's a sliding. So it's the same in all four links. Basically one because all are one. So this two is having similar phenomena at all these four interfaces. So they are all will be J1. And yeah, and this one is also J1. Yeah, so this one is J1 as well. So single degree because you need just one angle of movement to explain. And this one is of course J1 because it's just again to give you revolute pair. This one is J1. Yeah, so this one is J1 because it is also doing just one movement, which is just one angle. This is also J1. This is one angle. This one is J2 basically, as I said, because we need two. So at this particular joint, you can do two types of motions, J1 and J2 both basically. So that's why it makes it J2 basically. Yeah, so that's it. You just plug in. So the links and the joints of the mechanism are labeled as shown in figure 1.9b. So this is 1.9b. The number of links n is equal to 5. So we have identified 5 links, lower joints 5. So you can count those one there 5, and then number of higher pairs. So this J2 is equal to 1. So substitute values, Kurzbach criterion, and you have 1, right? So M value is equal to 1. For this mechanism, the mobility is indeed 1. So Kurzbach criterion is giving you the right answer, which indicates that Kurzbach criterion gives the correct answer for this mechanism. So the qualitatively you can understand, because if you slide this one up and down, yeah, so means this will move, this joint will move up and down. So this can oscillate like this. And this can of course slide up and down, and this can rotate, right? So now all these movements which I have highlighted, you can do by same way. For example, if I rotate this and leave all independent, you will still have same motion. So this will oscillate, this will move like that, and this will slide. If let's say I don't do that, I just move this part, for example, at this part, it will still do the same movement. So that's why this is a qualitative analysis. So Kurzbach is quantitative. This is qualitative analysis, which shows us that this mechanism is working basically. So this has the mobility of 1. All right, so that's it. So we will keep continue. So we have some more examples coming up next, and then we'll continue with that one.